Good evening. You are welcome to the fifth class in Chemistry 205. Today we will be looking at Group 7, that is the halogens. The halogen family comprises of fluorine, chlorine, bromine, iodine, and astatine. In this very particular class, we'll be looking at their occurrence, extraction, and uses. 2, we'll look at their general properties, both physical and chemical properties. 3, we'll be looking at the interhalogen compounds. And 4, we will look at the anomalous behavior or characteristics of fluorine. The chemistry of the halogens is very interesting and have varied application in our daily human endeavors. So there are so many of those things that we are going to be looking at in this very particular class. We'll also look at their applications of the halogens in our day-to-day activities. One thing about the halogens is that they have one electron short of the octet configuration. In other words, their outer electronic configuration is Ns2, Np7, which means that there are 7 electrons in the atom's shell. So they needed one electron to attain the octet configuration of the noble gases. Hence, because of the 7 electrons in their atom's shell, the halogens will prefer to gain 1 electron in the process of reacting with other elements. So its reactivity is also high at that level because of the ease of gaining an electron. In other words, they don't actually contemplate losing the 7 outer electrons because it is much more easier for them to gain 1 outer electrons. Their occurrence: fluorine being the first member of the group consists about 0.05% of the earth crust and is mostly appears in form of fluorspar. You find it in combined state in a compound that is generally called fluorspar. The formula of fluorspar is CaF2, CaF2. Sometimes we get it in form of cryolite. Cryolite is an aluminum fluoride salt of sodium. And you can also find it in form of fluoropyrite. Fluoropyrite is also a fluoride and phosphate compound of calcium. So these are the 3 major forms in which fluorine is found in the earth crust. Chlorine, which is about 0.013% of the earth crust, occur mostly as chlorides of sodium and other alkali and alkali earth metals. The salts are mined as well as found in sea water. And in sea water, chlorine is about 3% solution of the various salts, of which sodium chloride that is brine, is about 8.3% of the sea water. So mostly the chlorine is obtained through the electrolysis of brine. Brine solution, that is a concentrated solution of sodium chloride. Bromine, on the other hand, is found as bromides, and it occurs in sea water and dry salt lakes. It is about 2.0 times 10 to the power of minus 4% of the Earth's crust. While astatine, main source is ash obtained from burning seaweeds. Ash obtained from burning seaweeds. Astatine is found from ash obtained from burning seaweeds. And shale, C-H-I-L-E, that is saltpeter, in which it occurs as iodides, is found in form of iodide as iodides. Nowadays, it is extracted from brine. It's also extracted from brine. Acetine is a radioactive element with a half-life that is less than 1 minute. Hence, it occurs in negligible amount in nature. Acetine is a radioactive element. Its half-life is less than a minute. And it is found in negligible amount in the Earth's crust. An isotope of acetine, that is acetine 211, has the longest half-life of about 7.21 hours. And is obtained from bombarding bismuth with alpha particles. It's obtained from bombarding bismuth with alpha particles. And the equation is as follows. Bismuth 209 and 83 plus an alpha particle, helium 42, reacts to give you acetine 211 85, the atomic number 85, plus 2 neutrons that are given out, plus 2 neutrons that are given out. So when bismuth is bombarded with alpha particles, the resultant product is that an isotope of acetine 211 is obtained with neutron particles, 2 neutron particles given out. Now, extraction. Fluorine is extracted from electrolysis of potassium fluoride, which is dissolved in anhydrous hydrogen profile. Fluoride is dissolved in anhydrous hydrogen fluoride, while chlorine, on the other hand, is obtained as a byproduct in the electrolysis of brine, where chlorine and sodium are the main products that are released. So the chlorine that is released as a byproduct can also be collected. Bromine, on the other hand, is obtained by reaction of bromides with chlorine. Bromine is obtained by reaction of bromides with chlorine. A mixture of air and chlorine is blown through an aqueous solution of bromide at a pH of about 3.5. Chlorine displaces bromine in the air, and air blows it out of the solution. The air blows it out from the solution. And again, iodine is obtained by the oxidation of iodides by chlorine. It is prepared by treating brine with silver nitrate. The silver nitrate is precipitated as silver iodide. And this is possible because silver iodide is the least soluble of all the silver halides. So the silver iodide settles down as a solid. That is, if you have brom iodide reacting in the presence of silver nitrate, it will give you silver iodide. And if iron is added, the silver will settle down and ferrous iodide will be released out. The equation is as shown on the slide. Now, if we try to look at the uses, what are the possible uses of some of these elements? The main use is in the halogenation of organic and inorganic compounds. They are mostly used in the halogenation of organic and inorganic compounds, e.g., iodine, when dissolved in alcohol, serves as an antiseptic. And I'm sure we are aware of the use of antiseptics in cleaning wounds to prevent infection. Iodine is also present in thyroid hormone, and the deficiency of iodine leads to the formation of what is called goiter. So in order to prevent goiter, that is the swelling of the throat, in order to prevent goiter, deficiency of iodine, the salts, iodine is usually added to salts. That's why you hear most of these days, most of the salts that are sold in the market, you hear iodized salt. Iodine is added in order to prevent the formation of goiter in human beings. You also see toothpaste, mostly fluorides are added to toothpaste in order to prevent tooth decay by dental caries. So most of our toothpaste, you will discover that there is fluoride that is added to it. The essence of adding the fluoride is to prevent tooth decay so that our teeth does not get bad. Also, liquid fluorine is used as an oxidant in rocket fuels. That is before. In the olden days, liquid fluorine is used as an oxidant in rocket fuels. But this has been discontinued because of certain disadvantages that were discovered. We also know Teflon. Teflon, a familiar household product, which most housewives use in form of its coating on kitchenwares to make them not sticking. The kitchenwares are coated with Teflon so that it doesn't stick. It is a polymer of fatty fluorochlorinated or fully fluorochlorinated ethylene. There's also chlorofluorocarbons, which are used as refrigerants. Chlorofluorocarbons are also used as refrigerants. Now, most of these compounds I'm mentioning are interhalogen compounds. That is the compounds that is formed between halogen and themselves. In aerosol sprays, you also have the use of the halogens in aerosol sprays and in microelectronic fuels. Also, bleaching powder is a calcium oxychloride or a calcium chloride compound that is actually used for bleaching. And chlorine, in most cases, particularly in the oil, is used in chemical warfare, particularly in the First World War. Chlorine was one of the major elements that was used in the chemical warfare in the First World War. And most of the explosives we actually use these days, or you see being used in the war front today, actually are compounds of chlorine. They are compounds of chlorine. You also have the polyvinyl chloride. The polyvinyl chloride, which is also another compound of chlorine, is a very important product that is found in the market today and used in most of our petrochemical industries because of its non-inflammability and insulating properties. It is actually used as an insulator for connecting electric wires, making conduit pipes, and also things like DDT, dichlorodiphenyl trichloroethylene, is used as an insecticide. Though it has been banned from the market, but it still finds its use today, particularly on most of our soil and in most of our lands, because most of the farmers have not actually gotten rid of it. Even though it's banned, you will hardly see it in the market, but they still have where they obtain it. From the analysis of most of our soils, you still find some traces of DDT which are present, which indicates that still farmers still make use of this very particular compound, particularly for the treatment of insects on their farms. General properties. They all have 7 electrons, like I said earlier, in their atmosphere, with an ns2 np7 configuration. They are 1 electron short of the noble gas configuration, and they exist as non-polar diatomic molecules, and most of them are actually colored in nature. Fluorine, in particular, is pale yellow. Chlorine is yellowish green. Bromine is brown. Iodine is violet if it is in the gaseous state, or greenish, and is black if it is in solid form with shiny silvery luster. Except for iodine, which has useful biological uses, all other are actually hazardous and they are toxic. Except for iodine, which has found its biological use. Most of these other halogen compounds and also the interhalogen compounds are hazardous and they are toxic. That's why they found most of their uses, particularly in the weaponry, like the TNT or RDX. The TNT is an explosive, RDX is an explosive, and most of these explosives, part of their component contains either chlorine or fluorine, and these are halogen compounds. The only forces of attraction that exist between molecules is the weak van der Waals forces that binds the molecules together. That is the halogen forces that binds them together. They are weak van der Waals forces. The polarizability increases as you move down the group. Fluorine and chlorine are gases at room temperature. Bromine is liquid and iodine is a solid. Effective nuclear charge also increases across the periods. Hence, they have the highest ionization energy in that very particular period, because most of the period, the last but one element is the halogen. And that halogen at that very particular stage is having the highest electronegativity value. So they have the highest ionization energy in that period. The electron affinity is of the order of chlorine, is greater than fluorine, is greater than bromine, is greater than iodine, and it is greater than acetylene. Why is chlorine greater than fluorine? I'm sure should be the question at the back of our mind. Reason is that fluorine, because of the smaller electron affinity than that of chlorine, so as a consequence of its smaller size, it assumes a higher distance than that of fluorine. The electronegativity also increases across the period, reaching its maximum at the halogen level, because the moment it gets to the next level, that is the noble gases, it attains an octet configuration, is stable. So it reaches the maximum at the halogen level. Down the group, the XX bond dissociation energy also decreases. That is the bond dissociation energy of the fluorine and fluorine atoms linked up together. The halogen and halogen atom linked up together decreases as you actually go down the group. So when you found the interhalogen compounds, interhalogen compound has a form of degradation. You can have XF1, XF2, XF3, depending as you move down the group. There's the tendency of formation of many halogen atoms attaching themselves together. The reason being the availability of the d orbitals. Fluorine being the smallest member of the group, and not also having an the availability of d orbitals, the tendency of it to expand its octet is not there. But from bromine, iodine, astatine, because of availability of the d orbitals, they can be able to expand their octet, which means that they can be able to accommodate more donor atoms that will come to donate electrons onto themselves. So they'll be willing to accept that. So that means that they can have oxidation state, not limited to only 1 or -1. It can reach 2, 3, 4, or even up to 7. But their most common oxidation state is actually -1. The most common oxidation state is -1, which is much more peculiar to fluorine and actually chlorine. But as you move down the group, the tendency of that oxidation state also decreases down the group. Once more, I welcome you to this class. I welcome you to this class, and I hope to have a better participation in the next class when we shall meet again. Thank you very much.